Hi, and welcome to the video for Module 3 for Introductory iOS Development, where I talk about the assignment for this module. In this module, I've finally got you doing writing a program that does something useful. It's a loan payment calculator. And what I've asked you to do is given some loan terms, that is an amount of the loan, number of payments that are going to be made, how frequently the payment's going to be made, what the interest rate is, calculate what the monthly payment would be. And what I want to do in this video is sort of explain the basics of time value of money and how you can compute what that fixed monthly payment will be if you make it a certain number of times, will result in the loan being completely paid off at the end of the loan period. So let me get started with that. The key idea is actually in this cartoon. This character is Wimpy from Popeye. I don't know if anyone has ever read a Popeye cartoon or not, or if I'm just showing my age here. Wimpy was a character who loved hamburgers, and there's actually a very popular hamburger restaurant chain in Europe called Wimpy Burger for a long time. I don't know if they're still around or not, but this was a saying that Wimpy would make on occasion. I'll gladly pay you Tuesday for a hamburger today. And that's funny because the payment on Tuesday isn't worth the same amount, really, as the payment today would be. Money in the future is different than money right now. In particular, that's because you get paid interest for having money. So let's start. I want to start with the idea of the value of $1 today versus the value of that dollar a year from now. Surely I can write better than this. There we go. And if I have that dollar and I keep it for a year and I invest, say I put it in a savings account or invest it in, I don't know, a certificate of deposit or a bond or a stock that pays a dividend. At the end of a year, let's say any of those investments would have yielded me a 10% annual interest rate. At the end of a year, I don't have $1. I'll have $1 times 1.10, which is $1.10. And that's the equivalence that I want to set up. $1 today and $1.10 a year from now are equal things. You can move money through time with the recognition that whoever possesses that money as it moves through that time is due some sort of a rate of return on it. And what that rate of return is can depend on a lot of things. It depends on the fundamental a functioning of the economy. It depends on levels of inflation, which are also dependent on the functioning of the economy or misfunctioning of it. And the reason why people pay interest on money is because of in some sense you could think of it as a rent on the use of the money. I will loan you $1 for a year if you'll give me the dollar back plus some fee for using it. and how much of a fee I get depends in some sense on how much uncertainty there is. How likely do I believe you're going to pay me back? Because I'm not going to loan just you $1. I'll probably loan thousands of people $1. Some will pay me back, some won't. And hopefully in the end, I'll make some money. This is just all basic economics. I don't want to get into too deep of a sort of economic justification of the theory of interest. But because this is a computer science class, not an economics class, but um, this is the idea we're going to use to develop to figure out how much that loan payment should be. And the concept here, the interest payment, is the fee that's due to whoever is loaning you money to buy. And we're talking about the kinds of loans you would buy a house or a car with for this loan calculator. So extending this, let's say, what would the dollar look like at the end of 2 years? Well, it's the same amount as what we would have at the end of 1 year, except we've had it another year. So that would be the value at end of 2 years. And we can rewrite that. That's equal to $1 times 1 plus our interest rate. That doesn't look clear. Let me rewrite it. $1 times 1 plus the interest rate squared. And you can see that after n years, the formula would sort of obviously extends. $1 after n years is worth $1 times 1 plus that interest rate raised to the power n. And we can run this backwards. If $1 today is worth $1.10 at the end of a year, then what would $1 at the end of the year be? It's going to be the same ratio. $1 at the end of 1 year would look like $1 divided by 1 plus the interest rate. So that's an equivalence. Likewise, $1 at the end of 2 years. Today, I'm going to call this column the present value of that dollar. That is the value of it right now. And what we're doing, this is, and I'm going to call this a discount. So this whole thing is the present value of that dollar. And we're going to call this denominator a discount factor. Because you'll notice that it's what the dollar today, the dollar a year from now is going to be worth less than $1 because this number is bigger than 1. So this is going to get smaller. At the end of 2 years, you can probably figure out what I'm going to write. It's $1 divided by 1 plus the interest rate squared. So where are we going with this? How does the loan look? What are the transfers of money in the loan? So now, the amount of the loan is transferred. Let's see. Let me make 2 columns, I guess. Here, I want to have time. I want to have the lender and I want to have the borrower. And we're going to move money. Now, money goes from the lender to the borrower, the amount of the loan. That is, say, the price of your new car. And we're going to forget about down payments and things like that. We're going to assume you borrow 100% of the cost of your car. And what's going to happen is you're going to make payments back. And let's say you only have to pay back, typically you pay a car back or our house back once a month. But let's say that you're only making payments once a year to keep things simple now. So at the time 1 year, the borrower is going to pay the lender back a payment. We'll call the amount of the loan V, and we'll call the amount of payment P. And the borrower is going to keep making these payments at the end of each year. Till we get to the end of the loan. And let's say it's an N-year loan. And the idea, what we want it to be the case, is that the payments are such that at the end of, after N of them, the amount of the loan is paid off. And we're going to, but the payments aren't, the present value of the payments, so the sum of the present value of the payments has to equal the amount of the loan. So I can, if you remember the sum notation from the discrete structures course, I'm going to say that I have a function PV that computes present values of payments. And let's call the payments P1, and they're all equal, but I want to designate them, show that they're different in time. So I'll call them P1 through Pn, and we'll take the present value of each of those payments, sum them up. That has to equal the amount of our loan, V. So the thing that remains is to figure out what the present value of each of those payments is, and see if we can solve that for the amount of the payment. So we'll say over here, all payments equal amount P. And the interest rate on the loan, we'll say, is I. And I is going to be between 0 and 1. We won't consider interest rates greater than 100%. Typically, unless an economy is in hyperinflation or some kind of free fall like the Venezuelan economy is now in 2019, you don't have interest rates higher than 100%. So we'll just say that to make things simple on ourselves, it's between 0 and 1. And so, for example, a 10% loan, and that's an annual interest rate, I is going to equal 0.01. I can write that more neatly. So now that we have an interest rate associated with the loan, we know how much money in the future is going to be worth. A payment of amount P, I years in the future, is going to be worth P divided by 1 plus I. I'm sorry, let me use a different index here. If I'm going to use I for my interest rate, I got to use something else for my index variable. Let's use J. 1 plus I to the jth power is the present value of a payment P J years in the future. at interest rate I. So I can write that then. I can write that PV PI is this. And now I know how to write an equation I can actually solve to give me P, which is the amount of my payment. And that looks like this. The amount of the loan is equal to the sum from J equals 1 to N of P divided by 1 plus I to the power J, where I is the interest rate per period, and we have one payment per period. And in payments, loan amount is V, and so these would be the things you would be given: the interest rate, the number of payments, and the loan amount, and you want to calculate P. So you can do it from the formula above. P equals V divided by J equals 1 to N of 1 over 1 plus I to the power J. So this is the thing I'm asking you to calculate in Swift. The other pieces of the assignment for this exercise are just hooking up action methods and outlets and so forth and making the user interface work well. This is the model part of your calculation. This is the thing that the app exists for, to calculate this formula. So you're going to have to write Swift to do that. And it's not that hard. Just wanted to get you a little bit of practice programming in Swift. So hopefully this explains the things you need in order to do the programming exercise for this module. I'll see you in the next video.